right, so now we're talking about chapter 5. Chapter 5 is where a lot of fun stuff happens. We start actually considering the Klein Gordon equation, the Dirac equation, the Proca equations, their corresponding Lagrangians, and so forth. So let's dive right into this. This is going to be fun. So we're going to start off talking about the Klein Gordon equation, and we're going to spend the first 2 videos on the Klein Gordon equation. Then we're going to move into the Dirac equation, where I think I've split that section into 3 videos. And the Proca equation, I think, only has 1. And we're gonna go, the book continues to go deeper into these equations and sort of siphon out the physics out of them. And so this is gonna be really, really fun, I can guarantee you. So let's get started with the Lagrangian of the, for the Klein Gordon equation. Again, this is for scalar fields, right? So this is for scalar fields. The Klein Gordon equation historically has been the first equation proposed as an attempt to merge special relativity in with quantum mechanics, and unfortunately does not do very well when predicting certain outcomes. Nevertheless, this is a hallmark equation that everyone learns. And so let's get right into this. Right here, what I have is the Lagrangian for the Klein Gordon equation. Right? So this is the Klein Gordon Lagrangian, right? So sometimes you'll see N, L, K, G, and basically what this is it's the Lagrangian that when we do the Lagrange equations on this, we get the dynamics for a scalar field. And it's been proposed that the only scalar field out there is the Higgs field, and we'll get into that also. But let's get right into this, right? So we have this Klein Gordon Lagrangian, and we want to apply the Euler-Lagrange equation to this. And if you recall, the Euler-Lagrange equation looks something like this. So we have the Lagrangian, the derivative of the Lagrangian with respect to the field values, minus the derivative of the Lagrangian with respect to the derivative of the field values, equals 0. And we showed this. We didn't really show it. The Euler-Lagrange equations can be easily derived, and that's something I'll probably do in my Patreon page because that just eats up time for the playlist here. But anyway, so this is, again, the Euler-Lagrange equation, and let's start playing around with this. So let's take the derivative of the Lagrangian with respect to phi. Right, so that's really just going to be minus 2 times 1/2 times m squared phi, because what we're doing here is we're really just taking the derivative. We're taking the derivative of this right here, but the only thing that actually contributes to this derivative is this part right here, because these are derivatives. There's no derivative right here, and there's no derivative right here, but this one right here. Right, this one right here, this is going to be minus d mu, right? So that's this right here, times the derivative of the Lagrangian with respect to the derivative of the field values. Well, that is just going to be d mu, right? Because we're taking the derivative of this right here, and so this sort of is the constant in front of it, right? Like that. But not really, because we're going to have essentially what this is the derivative squared. So you bring over the square, the exponent. this is sort of the derivative squared. So I'm skipping a few steps in my head. This is sort of the derivative squared because we're taking, because it's the derivative times the derivative. These are just different indices. And the way you convert between the two indices, if you remember, is by using the Minkowski metric, right? And so the Minkowski metric in this case is just a ones along the diagonal. And so since it's just ones across the diagonal, with the exception of the differing signs, we really just get a moving of that exponent to here, and that's going to cancel with our 1/2. Similarly, these two guys are going to cancel like that. And so our this is equal to 0. So this is our Klein Gordon equation, right? And sometimes it's written like this: d mu phi, or no, minus m squared phi. And so in this notation, this is acting as an operator, right? But we won't get too deep into the idea of operators yet. But here it is. So this here is our Klein Gordon. I'll erase this. This here is our Klein Gordon. I'll actually spell that out because I'm realizing I actually haven't done that. Klein Gordon equation. Oh no, not equation. This is our Lagrangian. And this is our Klein Gordon equation. So this and this, these are very, very important equations, as we'll come across later. We want to make sense of these now. So how are we going to make sense of this? We want to make sense of the Klein Gordon equation first, and then we're going to try to make sense of its Lagrangian and what these physically mean. And this is what the book does. So we want to start off by considering a bunch of masses, and they're attached to each other via a string. Say, here's another mass via strings, and they're evenly spaced apart. And whenever, so we have sort of this membrane, if you will, of points, and points can be excited, like I have right here. Right here, we have sort of an excited point that's away from its equilibrium position. And we want to consider now, let's label a few things. What's the distance between here and the height here, as well as the distance here? Because we want to get a sense of what this excitation might look like mathematically. So we can use Pythagoras, right? So we use Pythagoras in this case, and we say that L squared is equal to the square root of what I'm going to call L squared plus Q1 squared. Okay. The reason I'm doing this is because I'm labeling this as a 1 and this as a 2, right? So this is just the height of value 1. That's what Q1 is, and then the distance, this distance right here is L. Okay, so again, we're just using Pythagoras. So then what we can do is we can say, well, we can factor out, this might be something you've seen already, well, we can factor out L squared, but to do that, we'd have to do this. Oops. Like that. Okay. What does this enable us to do? Well, this enables us to say L times the square root of 1 plus Q squared over L squared. Okay, this is really just algebraic manipulations on equations so far. Nothing too profound yet. Now what we can do is we could apply the Taylor expansion. Now we've done Taylor expansion before where, and I'm not gonna recap on Taylor expansion, but I'll sort of, once you do this a bunch, you can kind of just do it in your head. But the idea here is that the Taylor expansion is an approximation where we have L, we Taylor expand this guy right here, right? When we Taylor expand this, we get 1 plus Q squared 1 over L squared 2, with a 2 in the denominator there. So this is, I'll just write here, Taylor expansion. Right, and then what we can do is we just distribute, right? So when we distribute, we get that this is approximately equal to L plus Q1 squared over 2L. Okay, now, what does this mean? Well, if we take a look at this, this is, what did we say that this is equal to? We said that this was equal to, we said that this was L squared, L squiggly squared, right? And then when we, this is actually not squared, right? Because when we took the square root, I feel like I'll do it like this. When we took the square root, we got rid of the square on this side, right? So this is L, right? So L squiggly. Right? So that means that this here must be delta L. The reason that must be delta L is because we have a deviation from L to give us L squiggly. Okay. So, what this is saying is that, okay, so we have an equation for approximating the length of this right here, this distance right here. So if we know the excitation height and we know how far apart these scalar values are from each other, then we can get this value of L, or how much the deviation is, right? And so this is the deviation. The energy stored in this system, right? If we were to imagine these now as being attached by springs, like this. So this is the next thing we do, is we imagine that these are attached by springs. Each scalar is attached by springs like this. And so what does this mean? This means that the potential energy, V, between points 1 and 2 is equal to 1/2 K Q1 squared over 2L, right? Because this is 1/2 K delta L, or delta X. This is something you've seen before in our in not our courses, but probably something you've seen before in your classical physics class when you talked about springs, right? So this is the reason we did this, right? Is because now we can understand what the potential energy looks like. Okay. So we can generalize this now. Say we have 2 points attached to each other by a spring. That's not a spring. Attached to each other by a spring 1 and 2, and they deviate like this, where one height is Q1 and the other height's Q2. All right, so this height here is Q1 and this height here is Q2. Well, the potential in this case is just going to be V12 equals, again, just 1/2 K over 2L. Right, so that's this right here. The only difference now is that we need the height has become the summation of 2 heights, or not the summation, the difference of 2 heights, because this is in the positive direction and this is in the negative direction. Right, so we need to do Q1 minus Q2 squared. So we can begin to make sense of what the potential looks like, given that we have this right here, right? Because this all relies on this, because this was the form that delta L took, right? And so if we were to find now a Lagrangian, or propose a Lagrangian for a system like this, in which we had these sort of coupled harmonic oscillators, and we had n of them, right? So we had, there's 1, 2, say this was 3, this is 4 and 5, and so on. We had n of them. Well, our Lagrangian, what the book calls our non-coupled harmonic oscillator Lagrangian for this system, is equal to 1/2 m, a sum over I equals 1 to n, Q dot squared. So these are all of the individual kinetic energies of each one, minus 1/2 K n I equals 1 to QI squared. Right, so this is all of the potential energy for each one, right? So this is kinetic energy for each. This is potential energy for each. And then we have this added 1/2 K over 2L, and we sum over I and J in this case, and we go I minus QJ squared. Okay. And so what this isn't, so this is the potential energy that's associated with the coupling between 2 neighbors. All right, so PE for coupling. This is for each, and this is for each. Right, so we have a Lagrangian now that sums up everything we need to know for this n-coupled harmonic oscillating system. And so what we can do now is we can really just change our summations with integrals if we are considering a continuous system, right? So when we do that, we really just, by simply replacing all of this with integrals, we get that this is equal to, see, I don't want to mess this up, dx. Right, so I'm going to start off with this dx here, and we got to get 1/2 m. Here are the derivatives of phi, and again, they are a function of space and time. And we have 1/2 k squared like this, and this has to be squared. And then we have 1/2 rho, and this is the change in phi. Right, because this here is a change, or is a difference between the two. So this is the difference between two neighboring partners as you decrease the distance between them. So there is our non-coupled harmonic oscillating system in terms of an integral. And what we can do now is we can really just say, if we replace this now with, again, at this point, it's really just some mathematical manipulations, but we can say that this is dx times 1/2 mc squared, right? So I'm going to put a c squared in here, and I'm going to put d phi c dt, okay, squared, because the c squared is going to cancel out with the c squared on the bottom, minus 1/2 k phi squared minus 1/2 rho d phi dt, or not dt, dx squared, like this. And now what we can realize is that this here and this here, well, that's just part of a larger, here's just the temporal derivative, and here is a spatial derivative, right? So we can actually sum this up by saying that this is equal to, our integral dx, we sum our spatial and temporal, or we combine our spatial and temporal derivatives with each other to get a 1/2 mc squared d mu phi minus 1/2 k, like this. And what does this look like? This looks like the exact equation that we had come up with when we simply did the Euler-Lagrange equations from this Lagrangian, right? So this was our Lagrangian, and we came to here. Well, here, this is really just, it looks exactly like this, right? So so this system, this equation tells us that we're considering a system in which we have scalars attached to each other by springs, right? That this kind of confused me at first when I was, a long time ago, when I was initially studying quantum field theory, because merely just thinking about space in terms of points on springs was a little bit weird to me, right? Really what we're just doing here is we have an equation that models a system like this. And so we can say that this is what the dynamics of our field, of our scalar field, looks like. And it comes from this said Lagrangian, right? There's another way we can also derive the Klein Gordon equation, which the book doesn't go into, and I'm not going to go into it because the book doesn't go into it. But again, this is we proposed this Lagrangian, and we got this, and then we went ahead and we said, well, let's now consider a system in which we have points attached to each other by springs, and by considering this system, we essentially came to an equation that looked exactly like our Klein Gordon equation. I'm coming up on 30 minutes here, so I'll call it quits on this video. Again, if you like this content, please go to my Patreon page where I have exclusive only content for those of you who are invested in science and love to learn more about the natural world. And without further ado, I'll see you guys in the next one.